Okay, so in this presentation we're going to look at some of the fundamentals of software security with a focus on encryption methods and keeping things secure. Okay, so we're going to have a look at some basic functions inside the code that we'll use. So we're using ASP.NET and .NET in particular for this presentation. We'll look at the basic encoding methods that we can use, including base64 and hexadecimal. Then we'll have a look at some of the key or important private key encryption methods. Onto there we'll look at key hashing methods, which include MD5 and SSH1. And then on to public key encryption, so we'll have a look at how the RSA keys are generated. Then to look at Diffie-Hellman method, which allows us to communicate freely between two parties and no one else can actually determine what the end shared key actually is. Then digital certificates, we'll have a look at how keys can be distributed using certificates, look at secure functions, and then finally on to role-based security. Okay, so what's the fundamentals of encryption? So software itself needs to be secure, we need to make sure the data is secure, we need to validate messages, so more and more there is an increasing requirement to use encryption for many reasons. Might be to secure data, secure messages and validate them, might be to encrypt onto a data source, might be to authenticate a user for their identity, and so on. So more and more encryption is actually used to make things secure, also provide identity and to verify and validate that things haven't been changed. So it implies that we have some integrity around the principles of CIA, confidentiality, integrity and insurance. The three main classifications that we have for encryption include symmetric key encryption. With symmetric key encryption we use the same key to encrypt as we do to decrypt. So it's a little bit having a door with a lock where we open it with one key and we close it with the same key. So with symmetric encryption we encrypt onto our ciphertext from plain text, and then we decrypt with the same shared key. So algorithms include RC2, RC4, DES, and extension to this is 3DES, and the new standard which is used in many systems is AES. With asymmetric encryption we have two special keys that work together. So one of these keys can encrypt, and the only key that can decrypt is this other special key. So in this case we have two keys that are used in the process, one to encrypt and one to decrypt. Key methods that we have here are the classic RSA method, DSA, which involve factorizing prime numbers, which is a difficult task for a computer system. We have FIPS and Elgamal elliptic curve. So to give you some idea of the strength of these keys, we can see that an 80-bit to DES is equivalent to 1024 bits of RSA is equivalent to 160 bits of an elliptic curve algorithm. Our keys are generally getting larger as computing systems become more powerful. The last method that we have is a one-way hash where we can take some plain text and then make it into a ciphertext, and it shouldn't be possible to reverse it back again. This is often used to create a digital fingerprint or signature of data. Okay, so here we have the main three methods that we use: symmetric, asymmetric and one-way hash. Okay, so before we look at some of the methods that we're going to use, some of the encryption algorithms that we use, we'll look at some basic methods that we're actually going to use inside our code. So these are going to provide us with the little functions that we can use to convert certain things. The key ones and the basic process that we use in encryption is that we typically start with plain text. We then convert this into a byte array because memory itself is organized in a series of bytes. Each memory location represents one byte. So we typically have bytes, and we investigate each byte. So the actual memory itself becomes a byte array where we can access any part of the array. We can also get a memory stream where we can operate on it as a chunk of memory. From there we then encrypt from our byte array or memory stream into a crypto stream. So it's this crypto stream that provides us with the encrypted bytes within memory. It's often difficult to transmit that or in an email or to edit it at all or to view it. So we often convert it into a format which we can actually view. So in this case we would use base64, which is a convenient form to be able to represent binary information in a plain text format. Once we receive this, say, then we need to convert it back into our binary or our crypto stream. So we go through a decoder to convert it back from base64 into our crypto stream. We then decrypt. Obviously we have our keys here and we have our key there that we use. Normally a standard algorithm is used to encrypt and decrypt. From there we should end up with our memory stream or a byte array, and then we use a byte array to string conversion to be able to get the string back again. Okay, so this is the basic procedures that we typically go through when we're encrypting, from plain text all the way around back to plain text again. Okay, so the first two methods is a string to byte. So in this case we'll have a string, and what we'll do is we'll convert it into a byte array. Okay, so we pass a string to it. First thing we do is to pop off the string so that we get a character array. And so that will take FRED, say, and this is a string, and then convert it into an array with each character represented one in each location in the character array. Okay, so that fills char array. We'll pre-prep a byte array, getting ready for filling it up with the bytes that we have. So this basically does that, goes through the length of the array that's been created, and then we'll convert each character into a byte. Then we can return that back to the program. Okay, so this will take our string and convert it into an array of bytes. The other way around is that we want to have a byte array and we want to convert it back into our string. So we take byte array, convert it into a string. So in this case we just go around through the length of our byte array and then convert each of our characters into, in this case, a hex format for the string. And here we do the same, but this time we treat it almost like a file. So this represents the end of file here. We just keep reading from the buffer, the crypto buffer, until we get to the end of the file, or the end of the data within inside the buffer, and then we convert the character that we get, convert it from a byte to a character, and that fills up a string. Okay, so those are the two core methods that we'll use to be able to display and convert our strings. Okay, so the first thing we'll look at is how we actually encode our data, how we can convert it from one format into another. The two main methods that we use is that we take our ASCII, so that's what we understand, our plain text. Then we would convert that into byte values, so this represents an A, and this represents a B, C, and a D. So this is how the computer will actually understand it. We then encrypt something with our key, and then the output again is this binary data. So this data can be non-printing, so this character here, for example, could be a non-printing character. So when we displayed it or we tried to edit it, it'd be difficult for us to even view it. So we normally represent that in the form of either hexadecimal or in base 64. So this is a convenient format for us to be able to view and edit. With hex, we split up our stream and take 4 bits at a time and convert it to an equivalent hex character. So we can see in this case we have the value of 11111110, which is an E. Here we have a value of 2, so we have 1s, 2s, 4s and 8s. So in this case we have a 2 and an 8, which is 10. 10 corresponds to this one here, which is an A. Extremely common format is to use base 64. With this we take 6 bits at a time. So if we see, we have a 1, we have a 2, a 4, no 8s and a 16. So we have 16 plus 4 is 20, plus 2 is 22, plus 1 is 23. So we look over here and we can see that 23 corresponds to an X value. So that's a X there. So in this way we end up with a text format that we can actually view and transmit and so on, and it doesn't involve any non-printing characters as we see here. Luckily, .NET has methods which we can apply to convert our data to convert from a string to base 64 and vice versa. And so here is the converter here. So in this case we use the standard method from base 64, and in this one to base 64. So this is going to get this will get a value from data. So basically what will happen is that we'll read in message from a text box. We will then call up encode, pass that string in. The string will then get converted into a byte array using this method here, get bytes. And this is a standard ASCII here, 8-bit ASCII. And then from here we'll convert from the string into base 64. And we'll get it back as a string. And then we'll return that back. And we'll put that into a text box. Hopefully that text box will be here. So this is us getting the message here. And then we'll then, just to check, we'll take from that text box, call up base 64 encode, convert back into a string, and then hopefully what we'll get back is the same as what we've actually entered. Okay, so let's have a look at that. So we'll just pull up Visual Studio. Okay, so here we are, and we've prepared the page. If we want, we can just drag on our text boxes and mouse buttons and so on. Okay, so we can see this one here is called message. This one here is called TB encode. This is our button, so there's our button there. It's called button 3. We can have a look at the events on it, and you can see there's already an event in there. And there's what we've got inside the method, the event. And we've just prepared just a little method here, which does that, getting from message into message, and then does the encoding and then the decoding. Okay, so if our method hasn't been prepared, our event hasn't been prepared yet, we can just double click, and then we can actually just put in our code. So at any time we can run the debugger if we want. We can stop the code. Let's say we want to stop here. We'll just build that page. Okay, and that succeeded. And if we want it to run just that page, we can, oops, wrong one. We can just select that one, which is this one. Then we can just run it. Just takes some minutes. While that one's running, then we'll have a look at a real version that's running on a website. Okay, so this is our finished form. There's the table, and that's our code. So the first thing we should do is make sure that it's running okay. So we type in hello, and when we type in hello, we should get this result here for our base64. And you can see that that's the case. If we just type in hello with that, we should see, because the way it works is that only the first character is actually changing here. Okay, so base64 gives us a good method to be able to encode into a binary, into a text format. Okay. So we can do it the other way around. We can generate some random base64, and we can convert it back again, so it's just random characters here. If we wanted, we could take hello from here, capture that, copy it, paste it in there, and hopefully it comes up with the word hello when we decode. Okay, so what we'll do is we'll just start. Okay, so that's shown as an example of base64. Okay, so the next algorithms that we'll have a look at are the private key encryption methods. So as you remember, we have RC2, we have RC4, DES, 3DES and AES are all private key encryption methods where we use one key to encrypt and to decrypt. Okay, so this is what we have. We have our plain text. We go into our standard encryption algorithm, AES, 3DES and so on, and then we use a key to be able to create our ciphertext. We can then send that. Hopefully Eve can't decrypt what we're sending, and then as long as we've sent that key through or negotiated it in some way, then only Alice can actually decrypt back from the ciphertext to the plain text. And the way it does it is it'll take a whole block of plain text called the message block. It then encrypts each block one block at a time, and then joins these together to create a transmitted cipher block. So we have a secret key that we apply to make the cipher blocks. Each algorithm defines a certain size of message block, and these are known as block ciphers and are typical with the modern ciphers DES, AES and 3DES. The other type of encryption that we have is what's called a stream cipher. Basically it takes one bit at a time and then tries to encrypt it. These stream ciphers are very simple, but they are often weak in their security. So in this case we take a secret key. Then we have some random seed, typically known as an initialization vector, and that then creates an infinitely long key. The bits are then exclusive ORed one at a time to give the result. So a 1 and a 0 gives us a 1, a 1 and a 1 gives us a 0, and so on. In this way we get the output. The major problem with this type of stream cipher, as was seen by Webb, in that it can be easily crackable once the initialization vector wraps round after a certain amount of time. If the same initialization vector comes up, then it's possible for an intruder to be able to determine the secret key from it. Another problem that we have, if we took each cipher block, then we'd find that the same message would be creates the same cipher text. So in this case Eve could play back the cipher text again and again and play back the same message. So what we'll have to do is to add some salt into the equation to make sure that the block by block encryption differs in some way. So this is the way it would be weak to do this. We apply the key to each block so that the same type of message would actually be created with the same cipher block. And this is known as an electronic codebook. An improved method is to add some salt, in this case with an initialization vector, so that the encrypted block was actually different. So this is the case of Web. The problem with this is that the initialization vector is not applied to the other blocks. So I can see a weakness in this. If in this case we have segmented the image up, and in the way that an image would typically be split up into blocks, and then each block has then been encrypted. So we can see here without this by purely encrypting each block one at a time without feeding back from before, you can actually still see the image, because the same blocks with the same type of data are being encoded or encrypted in the same way. So even with AES we can actually see the message inside it. If we chain the output from one into the next, so that the IV vector is used initially to create an encrypted block, and then we take the output of that and feed into the next, then what we get is a completely randomized data set. So the key types of algorithms that we have for secret key encryption or symmetric encryption are 3DES, RC2, and now the new Raindal or AES encryption. Raindal won a competition which looked at creating an efficient encryption method which could support 128 and 256-bit encryption keys, and is now a standard. It was created by two Belgian creators, and they basically are the parts of their names, Rain and Dal. Okay, so let's look at some code. What we'll find in the code is that we have a crypto service provider in all the ones that we do. So in this case we have triple DES. It will create a new object for us here when we call up our crypto provider. What we'll then do is we'll take our key, so that's a key that someone adds as a text, and we'll create 24 characters for the key in this case, which is 192 bits. And then we'll have an initialization vector. In this case we'll make it static, but normally it would be random. And these two parts here will become our key and an initialization vector. So this is us creating the encryptor. This is the encryptor object that we're going to use. And then we create our memory stream, and this line here allows us to actually create the crypto stream from the key and the thing that we're actually going to encrypt, and then this just writes it to the memory. So the output of this will be our crypto stream. Okay, what we'll then do is we'll convert that into a string, as we've seen before with this method, and be able to view that. Then on the other side, what we'll do is that we'll do the same again, but we'll create a decryptor in this case, and then we'll decrypt the memory stream. Hopefully we can get back the original message that we sent, just to actually check it. Okay, so let's look at the code for this. Okay, so just while we're here, this is what the ASPX looks like, and if we want to have a look, okay, so here's the event on the button. Okay, so at any time that tells us what the C# code event actually is. So on click, and there's lots of other methods that events that we can actually use. These all relate to what we would see over here, and there's lots of properties. So let's undo that. So our ASPX file is the file that's run on the server and then renders the code, which renders the code into standard HTML. This defines the file which is associated with the ASPX page. There it is there. And then this defines the default class with inside the C# file. Okay, so it's this page here that really defines how the whole page is actually processed. Okay, so there we have TB message, we have encryption key. So the code that we need should be contained within here. So in this case we're just calling up check. So here's our code that we have. It's 3DES and so on, and that goes over the code. One thing that you'll notice here is that we've actually applied AJAX into it, which should allow us to be able to interactively update the page with that page refresh. Okay, so let's put in some text. Oops. Let's put it in a string. And there we go. So that's the ciphertext in hex, and then that's it decrypted. So we've actually proven that it works. If we use a weak key such as that, then it actually gives us an exception and says that it can't use that key. RC2 is quite similar. So in this case we have an RC2 crypto provider, roughly the same code in this case. Block size is 64 bits. And there we go. So we should find the bigger the message, the larger the encrypted stream, because it fills up a block or so. And let's have a look at rain dial. Okay, there's our encrypted stream, and then there's our decrypted, which should be the same as the message, hopefully. Okay, so that works. So again, it's just rain dial managed. Differences in the number of characters, which relates to the number of bits that we have, and the size of the initialization vector. So obviously this is a more secure code. We have 256 bits encryption, so which is 32 characters. That's just 8 times 32. And then you can see 16 characters for the initialization vector. The code is roughly the same as the other ones. Okay, so we've seen 3DES, RC2 and AES. Okay, so there's this one here is RC2. Within our code, we make sure that we have the using statement of crypto, system.security.crypto. Okay, so we can see here it's in system security crypto. If we ever need to, this one here we can see is in system security cryptograph again, and so on. Okay, so that's our RC2, and then the next one is rain dial. So we've looked at private key encryption, so the next thing we'll have a look at is public key encryption. And what we'll find is that public key encryption is based on the difficult task for a computer to factorize a value into its core prime numbers. It's an extremely difficult task for any computer to do, and up to now it hasn't been cracked. Okay, so with public encryption, we have two special keys, public and a private key. If Bob wants to send Alice a message, then Alice sends her public key. Bob then encrypts with that public key, sends over the cipher text, and then she decrypts it with her private key. Okay, so that's what's happened. Public key into ciphertext, and not even Bob can actually decode this or unencrypt it now because he doesn't have the keys here. So it gets sent over, and only Alice with her private key can actually decrypt it. Okay, so this is an example of RSA built into Microsoft.NET. We have an RSA crypto provider. But what we'll do is we'll have a look at how we actually generate the the public and the private key. Okay, so we'll go back to our code. And we'll have a look at 18. So what we do is that we select two prime numbers. Okay, so in this case we've generated 307 and 31. So to actually select prime numbers is a fairly difficult task for a computer, because it would have to search through by dividing by 2, 3, 4, 4 and so on. So what we normally do, and it would be very difficult because we deal with very large numbers, so normally our program actually has a pre-prepared list of prime numbers. So these can be extremely long, and these will have all the prime numbers which are known up to this point. So the computer will then just select from this list two prime numbers. So the next thing that will happen is that we take one away. We calculate n, which is p times q, which is our two prime numbers, and we also calculate phi, which is p minus 1 and q minus 1. In this case we get 20. Then what we do is we find the factors that could make 20, and a public exponent part is actually generated from the greatest common divisor between e and phi. Okay, so in this case we'll do that one. So we can see that's the value of n in this case with these values. There's phi, and then we have e. Next we use this equation here, and we use the modulus, which gives us the remainder, and this gives us the e value to the power of our n value, and then we can calculate this. In this case is 529. So then this gives us our public key, which is this, and our private key, which is this. So we can use the private key to be able to, we can use the public key for someone to encrypt for us, and then we use this key to then decrypt. So this shows us a very simple example here, using some simple numbers, and hopefully when we do the simple numbers, then our message is encrypted as that, and then decrypted as that. Okay, so that's the very simple code to be able to do that. Okay, so this shows an example of the generation of the code. Okay, so let's look at how that key looks. So what we'll find, so this code, if we had control of this server, then we'd actually be able to create a public and a private key. Unfortunately, the server will give us a security exception because it is possible on a shared website to actually determine other people's keys. So you can have a look at this link if you're interested. But we'll get an exception here when we actually try to use it, and saying that we don't actually have permission. So if we're using our own server, then we can get around that. So what we'll do is we'll just run a little Windows program here, and hopefully that will do. That will allow us to do it. So I've got a little RSA program here. Get some code, and there we go. So okay, so there's our private key. There's a D and N, that's what they look like, and our public key is E and N, so that's the key that we can distribute. This is the key that we keep secret. So when we apply the public key, then we get this cipher stream here. When we apply the private key, then we actually get the code back again. Okay, so that shows an example. Unfortunately, we've had to use the Windows program for that because of an exception, a security exception. Okay, so this is how it's meant to work. We see our public key and we see our private key, and there we then get our encrypted stream through RSA, and then that will give us our decrypted text just to test. Okay, so we've had a look at private key, public key. Now we'll have a look at the hashing methods, which include MD5, SHA-1, SHA-256 and so on. These methods are typically used to create a digital fingerprint. It's also used to verify that things haven't been changed and so on. So they're a very, very important range of functions. And really what they are is a one-way function. So mathematically we can go that way, but we shouldn't be able to go back the way. There isn't a mathematical algorithm that takes us back from the cipher text back into the plain text again. So we often use this method when we're storing passwords, so they can't actually be viewed. So in this case we take some text, we hash it, and then we get hash value, for which case that Eve can't actually guess it. So we have NT hash, MD4, MD5, SHA-1 and so on. It's used within Windows login, so the password is hashed inside the registry. So when the user logs in, it checks against the hash. In this case it's an MD4 hash. If you're interested, we have some basic code on that. That again gives us a hash certificate, and we hash value, and that's used in Windows NT, XP and Vista. We also see it on Cisco devices, where a secret password is hashed onto the configuration file, in this case with MD5. Unfortunately, it suffers from what's called dictionary attacks or rainbow tables. In this way, an intruder can set up a whole table with well-known words or commonly used words, and then to calculate the hash for each value. So in this case, this hash is equivalent to this one here. So then the actual original password is this one here. When we run this, is that another weakness that we can have is also that we can have a collision, and a collision is that the same hash signature occurs for a different text. We can also get it that a similar context of a message can actually produce the same type of hash signature. So it's been shown that on a good quality computer, the MD5, the same hash signature can be produced for a different message in less than a minute. With SHA-1, it's still many hours, but it is possible. Okay, so let's have a look at the code for MD5 and SHA-1. Okay, it's fairly simple. We'll just take from TB message, and then we'll display here. So I made these ones. So the update will come to these ones. So we'll have a look at the code that we have, and it's just a matter of taking our code here. So we're setting up the objects for MD5 and so on. We then convert our message into our byte array, and then from here we can take our byte array, and then we use the compute hash method of the MD5 object, and then that will create our hash message. We can use this byte to string static method. So static method is useful because it's only invoked once in the program and isn't associated with any objects. So it's a bit like a procedure or a function, passing the buffer, the byte array, and then it will return back a string. In this case, it returns back a string with hexadecimal characters so that we can view them. We could do the same for base64 if we wanted. Then we can do the same for SHA-1, SHA-256, and so on. Okay, so let's have a look at this running. Okay, so hopefully hello should give us this, and if we change just one letter, it completely changes the hash signature. Okay, so that's the code that we've used here, and you can see that the length of the digital fingerprint gets longer and longer, so it's much more credible to use SHA-512 than it is to use MD5. There are many more. There's less opportunity to create the same signature with different plain text messages. Okay, so we can also do the same with base 64. Okay, we often recognize base 64 with these equals at the ends. So hello from base 64. Hopefully our Ajax is working here, and it is. So there we go, that's the base 64 there, and then for hello we get another one there. Okay, so this is just using the to base 64 string to convert it into a base 64 format. Okay, so that was our crypto provider there that we used. One method to improve this is to add what's called salt. So salt, we won't always get the same hash signature. If we have a number of strings that we can add into the salt, then it'll produce an increased number of possible hash signatures. Obviously both sides will have to have that table to be able to generate all the salt values. So in this case my past might be salted into these three hash signatures. Okay, so what we're going to do is we're going to apply some salt. We're going to have different values of salt which will then be used to encrypt with the salt. Okay, so we'll take hello. And what that's done is take the salt value of Fred and then hashed it. This time it's taken the word Bill and then hashed it, so we see we get a different hash signature. So in this way we can set up a whole lot of salt strings. The program will then take a random value from there. This is the length of the array that we have for our salt strings. So it'll take a random value from there and then use that with inside the actual hash to give a different, so we can MD5 the salt value, add it on to the string, and then we take an MD5, so it will change each time. Okay, so that shows our salt values. Take a random there, encrypt it, add it on, and then we can then hash the whole thing. Another method that we can use, which is similar, is to use HMAC. So HMAC produces a hash signature, but can then be encrypted with a key. So on the other side must have the key to be able to generate the hash signature back again. So in this case, there's a message that was sent. Bob takes the message, encrypts it with his key, so we get a hash signature. So hello is received and the hash signature is also sent. Then Alice then applies the key and is able to get the same signature that she compares her HMAC with her key and also with the message that was received. If the two hash messages match, then she knows that the message hasn't been changed. Okay, so let's have a look at that. Okay, so we have a message, then we have a key that generates. So if we do testing 2, 3, and we do a key of hello, then it gives us a message of this, which is our SHA-1 message. And again, it's the same as we've done before. This time it's HMAC that we're using as a crypto provider. The one thing that we do is that we have our key now. We don't have an initialization vector in this case, and we just basically apply the key to produce the hash signature. Okay, so that was our HMAC example, and that was the code. So digital certificates are one of the fundamental areas that we have in security, and digital certificates carry with them either the public and or the private key. So they are a convenient way that we can actually send through keys and they can be transported. Okay, so it's one way that we can actually send a public key from one place to another, or we can put it in a repository called a PKI server, Public Key Infrastructure Server. Also, digital certificates are also used to sign messages and provide verification of identity. Okay, so this is what the certificate typically looks like. We have who's issued to, the issuer, the valid date, and so on. The key thing is that we have the public key in there, so we can see it's a 2048 public key. And then here's an example of our hash signature with thumbprint, and we can see it's a SHA-1 that we're using here, and that really verifies that the certificate hasn't been changed. Then we have the issuer, which is important because that provides the credibility that the user has actually been checked, or the person that's been issued to it. We typically get two types of certificates. One is one that we would buy and has the private key on it, so we wouldn't distribute this one, so it has both the public and the private key on it. When we export this one, which purely has the public key. So we can see there's no key on that one. There's no public key on that one, but there's no private key, but it does have the public key. The format we typically use, and we can see here, this is base 64. So this is how we can get a P7B format. We can get it as an email message and so on, and then we can import it into our certificate store. And that's what it looks like. Okay, so we've purchased the certificate, we then import it in, and it's on our certificate store. We can get other formats which are binary and have passwords associated with them, such as PFX and P12. These certificates themselves are X 509 version 3 certificates. It can also be used to, so we can see here that the certificate is sent from Alice to Bob. Alice pops off the public key, then encrypts, then over here, and then Alice should hopefully have her certificate, which is then uses a private key to decrypt it. So certificates are a good place to store our keys. They can also be used to actually sign things. It's out with the scope of this lecture, but basically Bob's private key is used to sign a hash of the message. That's then added on to an encrypted message using Alice's public key. So this all goes in together. On the other end, Alice decrypts with her private key, ends up with a hash. She uses Bob's public key from a certificate to then check that that has been hashed with his private key, and if the hash checks, then he's proven his identity. Okay, so let's have a look at some digital certificates. Okay, in this case we'll load up a certificate from the server. So in this case these are self-signed certificates. There's the public key within them. Defines the public key algorithm. There's the issuer, and there's the name, and that's what the actual base64 format looks like. This has been created with a package here which actually can create certificates. So let's have a look at what the certificate looks like. Okay, so there's its base64 format, and there's the certificate itself, and we can see here that it should relate to the basic details that we have in here. There's the issuer. This is an X500 format, common name, organizational name, and country, and so on, location, and that ties to that. The certification path is key. In this case it hasn't been issued by a root certificate organization, so it can't really be trusted. It's only been signed by the person who created it. Here's another one. We should be able to view that one. So these are X509 version 3 files. There's that one, and there's that one there. Okay. So we can install that certificate on our machine. We wouldn't really, because it isn't really a valid certificate, but we can actually see all the things in there. There's the public key, there's the thumbprint using SHA-1, and so on. There's a serial number there that we can match up to this one. Signature is RSA, and so on. Okay, so the code to read this is here. We just basically use this using in there, and then we can then use that to create from a certificate file to create this object, which is an X500 objects, and then we can then interrogate it for all the details. And that was 10. Okay, so let's have a look to see what that code is. Okay, so there are lots of other things that we can get from the certificate if we want. We've got most of the key details from there, but we can look at the date strings and so on and get the format. Okay, so if we're reading from a server, we would typically have to give the path name of it. Okay, so that's our example. Okay, so let's look at secure function evaluation. In this case, we get a classic infrastructure where we do not trust anyone, how we can make some decision on something without actually seeing the core data. So it's a classic problem that we have, and it's known as the millionaire problem. Two millionaires get together and actually they want to find out who's actually the richest without actually telling each other how much money they actually have. And neither of them trusts anyone else. So how do we create a function which allows us to do this? So an example might be we have Bob, Carol and Alice. There's certain votes for each person. Let's say we have these. And how is it possible for us to know the total number of votes without actually Bob revealing the votes that he got, Carol revealing hers, and Alice hers? So in this case, we can create an algorithm which actually hides the core data, but they can actually still communicate with each other certain values. So this has now been applied into areas such as online auctions, where many bidders could go into a system and then the actual bid is never actually released, but it can be determined which bid is actually the highest. Okay, so here's our example, and what we'll do is we'll go through the basic calculation for it, and then we'll have a look at the code. Okay, so let's generate some votes. What we want to do is to find out the total number of votes here, which is 11. So the first thing that Bob does is to create 3 random values so that his score, the total, will be his vote plus 100, which will be 101. Okay, so 5 plus 71 plus 28. Sorry, we've regenerated the votes now, so now it should equal 104. Alice does the same. In this case, she gets to 103, which is her vote is 100 and then 3. And Carol does the same. In this case, she needs to equal 107, so she's taken 105 and 1 and 1. So next, Bob gets Alice's second value and Carol's second value and adds it to his first value here to give the value of 36. Alice then takes Bob's second value, so Bob will tell her her value, takes Carol's third value and her own first value, and then gets that value. Okay, so we go through this, and then Bob, Alice and Carol announce their calculations. In this case is 314. We then take a modulo 100, which is 314 divided by 100, and we see the remainder, which is 14, and then hopefully that's the total number of votes polled. So in this case, Bob, Alice and Carol don't have to give away their original value, but we can still calculate the total number of votes cast. So here's the code here, and it's just the basic algorithm that we outlined. Generate some values here randomly for Bob, Alice and Carol. We then pass the values as we identified between them. So this is us generating 3 values which should count up to 100 in this case. So the last value is calculated by taking Bob's initial value and then vote, and then taking the 2 random values off it. Same again for Carol. So we end up with these 3 values here, and we can actually display them. Next, we can pass Bob 1, Alice 2, Carol 2, Alice 1, Bob 2, Carol 3, Carol 1, Bob 3, Alice 3. So that's what Bob gets, Alice gets, and Carol gets. We can then, these are the values that are displayed here. They then announce them to everyone. We add them all up, and then we take a modulo 100, and then hopefully we have the right value at the end. Okay, so that's shown an example of secure functions, secure function evaluation, example 17. This is just a little method that the event that generates some numbers. There's the generate values. That gives us our result. Okay, so this type of methodology is now used greatly in trusted computing, online voting, and so on, and it really gets rid of the trust element, that we actually trust someone to be able to collect values and trust them not to release them. So with these types of functions, then it's possible for us to communicate and to pass values without actually revealing our core data. So it might be used if we want to determine if someone is aged 18 or over from a database without actually releasing their date of birth. Okay, so the next little method that we're going to come across is an amazing little method called the Diffie-Hellman method, and it was invented mainly by Whitfield Diffie, and he came up with a method that allows two people to be able to communicate, or two parties to be able to communicate values to each other, and at the end of it they have the same secret key. Even if someone is listening to the communications, it's very difficult for them to actually find out what that key actually was. And it's used greatly on the internet, especially for tunneling and for creating session keys. Okay, so the dilemma that we have is that if we're using shared key encryption such as AES and RC2 and so on, how do we get the key from Bob to Alice without Eve intercepting it? And it was really solved by Whitfield Diffie, who came up with the Diffie-Hellman method, and it's one of the most widely used for passing secret keys. So how it works is that we agree on two values G and N, then Bob generates a random value X, Eve generates a random value Y. Bob calculates G to the power of X and then takes the modulo N. On the other end, Alice raises G to the power of her random value Y and takes a mod N. Bob sends Alice A, Alice sends Bob B. They do another calculation by taking B to the power of the random number, mod N, and the same on the other side, and at the end of it they should agree on the same key. Eve, although she's been listening, shouldn't be able to actually see what the key is at the end of it. Okay, so let's have a look at this. That's number 2. Okay, so let's generate some values, 31 and 19. And Bob has generated a random number of 3, Alice of 10 and Alice of 3. Now we'll calculate our A and B value. So that's G to the power of X mod N, and this one is G to the power of Y mod N. So Bob gets 7 and Alice gets 18. We'll then send over 7 and then 18, and now Bob does a new calculation, so hopefully when we press this button they end up with the same key. Doesn't look very interesting because we're just using very small numbers here, but let's see if we can get some larger numbers. Okay, so every time we do it, hopefully, sometimes because we're dealing with very large values we might get an overflow on the server, but we should be able to make it that every time we get the same key generated. And there we go. Okay, so this shows us some of the maths that we have here. So there's the power function, b to the power of x, converted to a 64-bit value, and then this takes a mod, the remainder of the division by n, and so on. Okay, so that gives us an example of Diffie-Hellman. If we want, we can look at the code. It takes a lot of minutes to show again. So that shows how we create a random number. This shows the calculation of A and B. There's all the maths that we had there, taking the g, n, x and y value. So it's g to the power of x mod n, g to the power of y mod n is the A and B value, so we put the A and B values in. Then at the end we pass the values over, and at the end we create Bob's key, which is b to the power of x. B was the value he got from Alice, and then mod n, and Alice takes the value she got from Bob, puts it to the power of y, and does mod n, and unbelievably they end up with the same key at the end. So it's quite an amazing little method, and it's used extensively on the internet. Okay, so that was the example. Agree on that, generate two random values, calculate this, calculate that, send them over, recalculate, and then we have the same matching key. So the last little thing that we'll look at is role-based security. That is used within .NET to provide certain roles to get certain rights. So it's possible to determine the role of the user and basically the rights. So it could be a system administrator or a guest or something like that. Okay, so what we need to do is that many applications get their rights from the operating system, which really isn't a very good method. It's much better to get the rights from some other way. So in this case we can use role-based security, that we can define that certain users are parts of a certain role, and they could be part of multiple roles if they want. So in this case Alice is part of the guest role, and Bob and Carol are part of the admin role. So there's several ways that we can define the authentication with built-in windows. So that gets the rights from the domain. We can have passport authentication, such as using card space and so on. The form space allows us to be able to add in a username and password for a page or pages, and we can also have IIS authentication. The code that we can use to be able to get that is called the Windows principle. So in this case we can actually find out what the role is of the person who's using the software, and then we can check against certain inbuilt roles, in this case such as the administrator. Okay, so there's lots of other things that we can get. We can check if the user or process is anonymous, have they been authenticated, are they guests, are they system users, and so on. The basic built-in roles that we have include guest user, power user, system operator, and just a general user along with administrator. So we can use this to be able to see what the role is and get them certain functions. So in this case we check to see if they're an administrator. If they are, we'll check that message. If they're not, then we get that message. Okay, so let's have a quick look at that one. Okay, so it's very simple. Windows identity gives us our basic identity that we have, and then the Windows principle will be able to determine our role. Okay, so we just run that, and we can see here that we're not an administrator, and this is the current service, the current ID. So we can see here we're running it through a web page, so that's why we have a very low access rights there. Okay, so this has provided us with a basic introduction to some of the secure software methods that we can have. We've went through basic encryption methods, encoding, Diffie-Hellman, digital certificates, secure functions, and finally role-based security. Okay, thank you.